do some kind of introduction to both the entanglement entropy and the entanglement spectrum. So remember, I think you've heard a lot about topological phases and of course a lot about fractional quantum Hall effect. So one of the surprising feature of a topological phase is, for example, if you change the genus of the surface you're working on, you will change the degeneracy of the ground state. And there is no way you can distinguish between two degenerate ground states by any local measurement. So that's the reason why people use topological phases to do topological quantum computing. You will be protected by construction from any local perturbation. So that's great, but actually there is a drawback. If you think about how to identify a topological phase, especially if I give you some microscopic model. Think about Landau level plus some interaction. And I ask you, okay, take that filling factor and try to see if you have this phase emerging once you have electron and Coulomb interaction in the lowest Landau level. And actually, it's not that trivial. And one of the reasons is if you want to use some kind of local order parameter, you're screwed basically, because topological order actually prevents to identify the phase by just a local measurement. So we need other tools to try to probe a topological phase. So in the field of strongly correlated system and topological phases, numerical tools, numerical simulations are a very important ingredient. Just to understand how these phases may emerge in your microscopic model. So if you do a simulation, you have two goals to achieve. The first one is, well, you need to convince yourself, and actually also to convince the referees, that what you see in your finite size calculation, numerical calculation, is actually the emergence of that specific topological phase. So that's the first goal. Well, the second one is you want to try to minimize your efforts because you're lazy or French. That's two options, or just because actually quickly you will be stuck. If you do any many-body numerical simulation on a quantum system, you know that the Hilbert space will grow exponentially with the system size, with the number of particles. Think about a system of spin 1/2. If you have n spin 1/2, the Hilbert space dimension grows like 2 to the power n. So if you take n equal, let's say, 32 spin 1/2, you already need like, I don't know, let's see, it's like 8 gigabytes only to store the information about the ground state. So yeah, quickly you will be, we'll be stuck with a very small system and we'll try to figure out, okay, this is the phase I'm looking for. Moreover, most of the time you will only access the ground state of the system, maybe like the few first excitations, but that's it. So you want a tool that, for example, only by looking at the ground state will tell you, okay, is it the phase that I'm looking for? So one way to do that is to use overlaps. Let's say you have a model wave function like the Laughlin state, and you do some numerical simulation using electron and Coulomb interaction. You can get the ground state at filling factor 1/3 and compare to the Laughlin state. You just compute a scalar product and you will get a number between 0 and 1. A number that will decrease if you increase the number of particles. So you have to decide, is it a good overlap? Is it a bad overlap? I will tell you in this lecture like what kind of argument you can make to decide if it's a good or bad overlap. But it's just like a number. So you have to make a threshold and say, okay, this one is a good overlap, this one is a bad overlap. You can use, of course, not local order parameter, but global order parameter. Think about the ground state degeneracy. That's the first test. Try to change, so go from the plane to the torus and see how it affects the degeneracy of the ground state. If you have not, for some topological phase, like the Laughlin state, if you work on the plane, it's just a single ground state. If you do the same calculation on a torus, it's a threefold degenerate ground state. You can try to play with a boundary condition, like the flux insertion and stuff like that. So that are some tools that you can use to probe your system. But actually, there was, like a few years ago, another way to try to extract information about these topological phases, and only by looking at the ground state. And this comes to the notion of entanglement entropy. The key point here is, let's say you take your system and you cut it into two parts, let's say A and B. So you have your ground state, and you cut it into A and B, and you try to characterize the entanglement between the A part and the B part within the system. And what we will discuss today is there are some, if you look at the behavior of the entanglement entropy, which is just a way to characterize the entanglement between the two parts of the system. Well, if you look at this quantity, you can access information about the nature of the excitation of the system, and only by looking at the ground state. So that's one of the concepts we'll look at today, and the other one is the entanglement spectrum, which is actually quite related. It's the same kind of setup. So take the ground state, cut your system into two parts, and you will look at the reduced density matrix when you trace out the density matrix of the ground state corresponding to the ground state when you trace out B, and look at what's going on for A. Okay, so here you have the summary, the overlook of what I will talk about in these lectures. So today I will focus on the entanglement spectrum and the entanglement entropy. I will talk about the simplest topological phase that you can write down as a many-body system, which is the AKLT spin chain. I won't talk about fractional quantum effect today at all. And I will show you the connection between the story of entanglement spectrum and matrix product state. And you will see that all the information that we will extract from this concept of entanglement spectrum is actually tightly related to a very efficient way to encode information about a quantum wave function. So tomorrow we will talk about the simplest example beyond the 1D system, like a 2D system, and we will see how we can observe the edge mode excitation, the edge mode of a system, just by looking at the bulk wave function and through the entanglement spectrum. I will do the full calculation for the integer quantum Hall effect, and then we'll talk about the case of chain insulator, which is the simplest topological insulator that you can build. So then I will address the question of more non-trivial topological phase, namely the fractional quantum Hall effect. I will talk about different way we can compute an entanglement spectrum, because you have more than one way to cut your system. Think about, you can cut in real space, like in this picture, but I can also work in momentum space. And I cut in momentum space into two. It's two different ways to cut the system, and you can extract two different kind of information. We'll talk about particle entanglement spectrum, which is another way to cut it. And then, depending on the time I have, I will either talk about fractional chain insulators. So chain insulator, when you add interaction, you get phases which are quite similar to fractional quantum Hall effect. Or I will talk about matrix product states for fractional quantum models, for fractional quantum model state, like the Delfino state, for example. Okay, so let's start these lectures with, unfortunately, a bunch of definitions and notations. So entanglement entropy and entanglement spectrum. So first, let's consider a single n-body quantum state, psi, that we can decompose onto an orthonormal basis. Let's call this basis lambda. So you can write down your state as sum over all the configuration, some coefficient C lambda times lambda. Now let's assume that we can write down all the lambdas as a product of two orthonormal bases, mu A and mu B. So where mu A and mu B are orthonormal bases. So if you want to make this story more concrete, let's think about a spin 1/2 chain. So you have your spin 1/2 chain, it's like this. Of course, on each side you have a spin 1/2. You can be spin up or spin down. So the lambda will just be this configuration and up, up, down, down, up, down, up, up. And now I can decide to cut my system into two parts, like this one. A and B. So I can write this state as down, down, up, tensor product, down, up, up, up. Okay? So in this example, my many-body basis here will be the many-body basis that you build for your 8 spin 1/2. The basis for A will be the basis for the 4 left spin 1/2, and the mu B will be the basis for the right 4 spin 1/2. Good. So okay, good. So I can also decompose my state psi onto the many-body basis built as a tensor product between the A and the B part. So it will be a sum over mu A, mu B, C mu A, mu B, mu A, tensor product, mu B. So we define the entanglement matrix. M, where the matrix elements are M of mu A, mu B. It's just this coefficient of the wave function, C mu A, mu B. Let's say this Hilbert space has a dimension A plus B. This one has a dimension A. This one has a dimension B. So you see this matrix as a dimension is time A by time B. So once you have such a matrix, be careful. I mean, in principle, there is no reason for the dimension of the subspace A and the subspace B to be equal, right? So these two numbers can actually be different. So the matrix M is not a square matrix. It can be in general, it's a rectangular matrix. So you can perform a singular value decomposition, or SVD, on this matrix. So you can write M as U, D, V dagger. So U is time A times the minimal, the lowest of the two values, dime A and dime B matrix, and which satisfy U dagger, U is equal to 1, would just mean that the rows of U are orthonormal. V is a dimension B times, once again, dim A time B matrix, which satisfy V dagger equal to 1. So it has orthonormal. I mean, if you look at the rows of the V matrix, they are orthonormal vectors. And D is a diagonal square matrix, which has a dimension min of dime A, dime B, and all the entries of D are positive numbers. So you can write them as, can you see what I write here, or should I write somewhere else? Everybody see what is written here, or, I mean, apart that it's badly written, but so I can write them as exponential minus psi I over 2, right? Taking psi I equal to infinity as an option. If I have a 0 in the diagonal, it will just mean that I take the psi to be plus infinity. Okay? So now that you have the SVD, you can rewrite your wave function in a slightly different way. Sum over I that goes from 0 to the min of dime A and dime B of exponential minus psi I over 2, so the entries of the diagonal matrix, and the tensor product of two vectors AI tensor BI. So look, it's the summation over I, and you have the same index for this state and this state. So, and I give you the definition of these two states. AI is just the sum of a mu A, U dagger, I, mu A, and B is sum over mu B, U, V dagger, I, mu B, right? Just if you use the definition of the entanglement matrix here, use its singular value decomposition, you can rewrite your wave function this way. And you can see that due to the properties of U and V, you have that UI, AI, AJ. So if you take two states here, they are orthonormal, and same story for the state. So this is called Schmidt decomposition. So if you take any quantum state, and any quantum state, and you want to make a partition into two parts, A and B, you can always rewrite your state as a sum of positive numbers and a tensor product of two states, one living only in A, one living only in B, the same index here, with where these states are orthonormal states, just by using the SVD. Okay. Unfortunately for you, the first half hour is going to be boring because it's just formula, but then we will do some physics, don't worry. We need these formulas, so. So now we can construct the density matrix. So it's a zero temperature problem, just a pure state psi, so that's the density matrix of the system. And we can compute the reduced density matrix rho A by tracing out over the B part. So it's a partial trace over B of the density matrix rho. You can also define the same way a reduced density matrix for the part B, which would be just the trace, the partial trace over all the degrees of freedom that you have that made your A part of the density matrix. So now using the Schmidt decomposition, we can actually rewrite this reduced density matrix in a very nice way. So it's just the sum over I. Once again, I goes from 0 to min of dimension of A, dimension of B, exponential minus psi I, AI, AI. So the state that you have for Schmidt decomposition, the reduced density matrix rho A is already diagonal on this basis, right? So you can read out the spectrum of the reduced density matrix just by staring at this formula, right? The spectrum of rho A is just the exponential minus psi I. It's a reduced density matrix, so all the eigenvalues, they have to be positive, and of course, they are positive because it's just the exponential. You can also do the same exercise for rho B. Once again, the spectrum is directly here, and it's exactly the same spectrum than rho A. Right. If you start from a single ground state, you compute the reduced density matrix for the part A, or the part B, you get the same spectrum. So that's why you can focus on, for example, rho A. Let's say rho A, the dimension of the Hilbert space for A is smaller or equal to the one of B. It's enough to look at this one. So now I will always assume that the dimension of A is smaller than the dimension of B. So the entanglement spectrum is just the spectrum of rho A. Actually, if you want to be a bit more fancy, the entanglement spectrum is just the set of the psi I. So that's the definition of the entanglement spectrum. It's the spectrum, or the log, minus log of the spectrum of the reduced density matrix. Remember, anytime you do numerical calculations, or actually even analytical calculation, when you have numbers, you have a spectrum, you should always try to find the good quantum numbers. You want to put labels on your energies or your levels. So what are the good quantum numbers here? So let's assume that you have an operator O that you can decompose onto OA plus OB. So if you think about the example of the spin 1/2 chain, take O to be the sum of all the SZ, right? Think about O being just the sum over SZI, or SZN, let's say, and to the number of spins. And then, of course, you can decompose into something like SZN belonging to A plus SZN into B, right? So that's a simple example of an operator, which is just a sum of something acting on A and something acting on B. So if you have the property that O commute with rho, which if rho is a single, if you have a pure state, so rho is just the projector on psi. If psi is an eigenstate, is an eigenstate of rho, of O, then you have this property, right? Just a trivial statement here. But you can have more complex example where you take not a single state, but you take a superposition of projectors over a degenerate manifold. So the only property that matters for O is actually that O commutes with rho. If you do have this property, then you can show that by taking the trace of this identity, so you get 0, which is equal to trace over B of O A rho plus trace over B of O B rho. So I can pull the trace inside the commutator here, and we'll get rho A, OA with commuting with rho A by definition of rho A. And here it's the trace, so it's a commutator on B, so it's just 0. So what I can show here is that if I have this property for an operator O, so that I can decompose a sum of something acting on A, something acting on B, if O commutes with the density matrix, then OA will also commute with rho A, which means that I can diagonalize simultaneously rho A and OA. So if you think about this example of the spin, it means that all the levels, all the numbers I have here in the integrated spectrum, I can put as a label the value, the sum over SZ, so the projection of the spin, of the total spin on the z-axis. So okay, enough formula for the moment. Let's look at one example. The simplest example that you can imagine is a spin 1/2 chain with only 2 spin 1/2. So 2 spin 1/2. So the most generic state I can write down will be just a linear combination of the up-up, the up-down plus down-up plus down-down. So if I want to draw a nice picture of my problem, this is what I have. I have my system with 2 spin 1/2. And I will do is to cut the system into 2. This will be the part A, and this will be the part B. Right? For this generic state, I can write the entanglement matrix. It's just sorting all the coefficients and putting them into a matrix. So it will give me C up, up, C up, down, C down, up, C down, down. Right? So now this is the entry for B up. This is the entry for B down. This is the entry for A up. And the entry for A down. Right now I've done nothing really spectacular. It's just rewriting this information into the entanglement matrix. So you can start with the first example. Let's say psi1, which is just the product state up, up. So the entanglement matrix for this one is trivial. It's just 1, 0, 0, 0. It's a product state, so it's already in the Schmidt. It's already Schmidt decomposed, right? We don't have to do any additional work here. We can read out the spectrum for this one. So as I said, we can use SZ, which is just the sum of SZA and SZB. These two guys, that's just a projection of the spin along Z for A, that's a projection of the spin along Z for B, and that's the total spin of my system. And I can use SZA to label my entanglement spectrum, the state of my entanglement spectrum. So usually what people will show is entanglement spectrum, where I put the psi I as a function of the quantum number that I use to label my levels. And there will be SZA can take 2 values, 1/2 and -1/2. And for this example, there is a single non-zero eigenvalue, which is equal to 0. Remember, psi1 is already, it's 1 times up, up, so that's the Schmidt decomposition. In the Schmidt decomposition, it's exponential minus psi I over 2, but since this is 1, the psi is equal to 0. Good. Next example. Let's do something more tricky. Take the singlet state. So the spin 0 that you built out of 2 spin 1/2. So psi 2 is 1 over square root over 2. Up, down, right. Okay, good. Minus, down, up. So that's one example of an entangled state. The entanglement matrix is a bit more tricky here. It's 0, 1 over square root of 2, minus 1 over square root of 2, 0. So it's not written, I mean, you have to perform the SVD on this one, but the SVD is actually quite trivial. You can write it like this, for example, 1 over square root of 2, 1 over square root of 2, 0, 0, 0, minus 1, 1, 0. So now if you look at the Schmidt decomposition of this state, you will get 1 over square root of 2. It will be plus spin up plus spin down and 1 over square root of 2. Remember that all the coefficients here have to be positive integers. It's plus up, tensor product, minus down. Right, so these are, remember the AI and the BI, so that's A1, B1, A2, B2. And once again, you can read out the spectrum of the resistance matrix just by staring at the Schmidt decomposition of the state, and you will get something a bit different from the previous one. Let me use, so that's for psi 1. And this is for psi 2. And the value is actually log 2. Right, so just one, so that's the simplest calculation that you can imagine for Schmidt decomposition and the entanglement spectrum. The first thing we should observe here, it may be a trivial statement, but if you look at the entanglement spectrum of these two states, so one of them is a product state, the other one is a singlet state, so mostly one of the mostly entangled states that you can build out of two-spin half. Well, just by looking at the entanglement spectrum, I can tell you if it's a product state or not. If I have a single level, then I know it's a product state. If I have two levels, my system is entangled. A and B are entangled. So that's also something I will stress a lot in the whole story of all this business entanglement spectrum. The nice feature here is that we will count stuff. Counting is like using integers, and it's really nice. When you have a continuous number, think about the overlap. It goes from 0 to 1. So you have to wonder if 0.85 is a good overlap or not. If you have 0.84, is it a good one? 0.86? When you count things, like here I have one level, here I have one level, here I have two levels. It's very simple to make the distinction between the two cases. And I hope I will convince you that for more generic case, it's really helpful to count stuff instead of just trying to figure out if a long number is a good one or not a good one. I have just something else to say about here story. Nope. Let's say we have still 5 minutes, maybe. Any question? 0? Oh, good. So now that we have defined the entanglement spectrum, let's define the entanglement entropy. So if you want to quantify the entanglement between two parts of the systems, you have like tons of ways to do that. So today we'll mostly focus on the most used one, especially in condensed matter, which is the Neumann entanglement entropy. So the Neumann entanglement entropy, or for short, I will just say entanglement entropy. But you have more generic. You have more entanglement entropies than this one. So in this case, it's just a trace over A of rho A log of rho A. I can use, so I know the spectrum of rho A, so I'm able to, it's quite easy to compute this entropy, just the sum over I of the psi I exponential minus psi I. Right? Or if you prefer directly to work, if you set lambda I equal to exponential minus psi I, so these are directly the eigenvalues of the reduced density matrix and not minus log. You also get the following formula: minus I, sum of I, lambda I, log of lambda I. You can also define, so that's the entanglement entropy for the part A. You can do the same exercise for the part B just by taking the reduced density matrix rho B and tracing out over B. You use, once again, since the rho B and rho A, they have exactly the same spectrum, it's not a surprise that you get exactly the same entropy for A and B. So SA is equal to SB. Remember that if you take a pure state, so if you do the calculation for the full density matrix, you just get 0, right? It's a pure state. There is a single eigenvalue in your density matrix, 1, so the entropy is 0. So the entanglement entropy of A plus B is equal to 0. So actually, that's why in general you have that S, the sum of the entropies of A and the entropy of B, is not the entropy of the sum. It's called strong subadditivity. And you see immediately that this quantity allows you to measure the entanglement between two parts of the system. Imagine that your ground state can be written down as a tensor product of a state that lives only in A and a state that only lives in B. If you have this property, so if this, then you can show that SA is equal to SB is equal to 0. So if you have a product state, if you have no entanglement between the part A and the part B, the entropy will be 0. Okay, so I think it's the perfect moment to have a break, and then we will discuss about what's going on for gap phases and topological phases when you do the calculation of the entanglement entropy. So let's come back in 10 minutes. Okay. Perfect. So one thing, my handwriting is really poor, as you might have guessed. So this was an equal, right? If you take a product state, the entropy for A is equal to the entanglement entropy for B is equal to 0, right? It was an equal. So someone asked me the question. Next point, this is the log ln. I know it might be like the French way to write the logarithm. So if you prefer, just replace ln by log. Okay? Good. So now we want to look at the entanglement entropy for certain type of systems. We will focus mostly on gap phase. Once again, topological phases are gap phase, so that's exactly what we want to address right now. Before talking about gap phase, I would like to give you the example of a random state. The reason why is the following. I already tell you that if you want to compute an overlap, you have a model wave function and you have some wave function produced by your exact delimitation code or whatever for a more realistic microscopic model. So the easiest way to compare these two wave functions is just to compute the overlap between the two. You get a number between 0 and 1. And the question is if the number that you get corresponds to a good overlap or a bad overlap. There is actually, it's quite simple to get a lower bound for what is a bad overlap. What would be a bad overlap? Let's say it's like a monkey test. Take two monkeys. They just have to write down like one wave function, each of them, and then you compute the overlap between the two wave functions. So if you have a Hilbert space of dimension d, say capital D, and psi1, psi2, two random states. And if you have a many-body basis, remember the lambdas that I was describing at the beginning of this lectures? So this is a many-body basis. You have to define the state, you have to give all the c lambdas. So just take random values for the c lambdas. So that's a way to generate a random state. Now, if you do that, the average overlap will go like 1 over the dimension of the Hilbert space. So the thing here is you should not cheat, right? I can always increase the size of the Hilbert space by not considering additional symmetries. So take all the symmetries of your problem. So you know exactly if you look at one sector with all the right quantum numbers, you know the dimension of this subspace. Now you know that if you pick two random states within this subspace, the overlap will go like 1 over d. So if you do any numerical calculation, you compute the overlap between two states, and you get something of the order of 1 over d, you're as smart as a monkey. So we will try to improve that a little bit. Actually, it's not completely useless to think about random states. What would be the entropy, the entanglement entropy of a random state? Well, actually, it's something that you can compute. So take a random state. I will take the following limit, where the dimension of the subspace corresponding to the B part is larger or equal to the dimension of the subspace, the A part, which has to be much bigger than 1. So in this limit, you can prove that the entropy will be like, so do you prefer ln or log? Any preference? ln, okay, good. One answer, woo! Dimension of A minus the ratio between the dimension of A 2 times the dimension of B. Right, so that's a generic statement. So in the notes you will have all the references, right? So if you want to get the mathematical derivation of this one, you will find the reference. Maybe some useful limit. Imagine that your part A is not like a tiny part of your system. Let's say you have 2,000 spins, 1/2, and you look at the entropy of a group of 100. So this will just be something like the log dimension of A. So what is the physical meaning of this entropy? Once again, take the spin 1/2. Let's say you have VA spin 1/2. You know that if you have VA spin 1/2, the dimension of A will be 2 to the power VA. Dimension of B will be 2 to the power VB if you have a VB spin 1/2 for B. So roughly, SA goes like VA log 2. VA is what? It's the number of spin 1/2, but it's also the volume of the part A. So if you take a random state, you compute the entanglement entropy for this random state. The random state obeys a volume law, which means that if you increase the volume of your system A, the entropy will grow linearly with the volume. So that's going to be really different for gap phase. So now for gap phases. So let's call eta the correlation length of the system. And we cut the system into 2 parts, A and B. So we cut it like if you have, once again, we can think about a spin chain or whatever, any 1D lattice model. So that's going to be A, and that's going to be B. Or you can think about a 2D system where you cut this part A, and this would be the part B. Right, that's the way we cut our system in the physical system into 2 parts, A and B. So for one-dimensional gap phase, what you can show is that the entanglement entropy of A is actually a constant. You have many works on that will show this. It's an exact mathematical statement. You can prove that there is a upper bound for this constant term. So that's quite a different feature from the random state. If you take, once again, you take a 1D system, you take random state, you will get that the entropy grows linearly with the volume, which will be here the size of the length of A. If you have a gap phase, this entropy is a constant. For higher dimension, in that case, the entropy will grow linearly, not with the volume, but with the perimeter of the boundary between A and B. So L is just the length here. And this one is a non-universal constant. once again, I will still focus on gap phases. So I think for this one, so this one is mathematically proved. This one, I think it's more conjecture. But physically speaking, it's quite intuitive why they should grow with the perimeter and not the volume of A. If you have a finite correlation length, it means that all the entanglement here between A and B will actually occur in a region which is like this. So the volume of the region where you have the entanglement between A and B is something of the order of the correlation length times the perimeter of the system. So of course, the coefficient here, alpha, will depend on the correlation length. But if you increase the size of A, you will just increase linearly with the perimeter. So this is called the area law. Just if you, I mean, there is like right now lots of discussion about many-body localization, and many-body localization is actually about trying to figure out if the states, when you have disorder in interaction, if all the eigenstates of your spectrums obey in average to the area law versus the volume law. So this distinction between volume law and area law is really, really important. Actually, when we say that the 1D gap phase is just it's a trivial case of an area law, right? In a one-dimensional system, the boundary between A and B is just a single point. So the perimeter is just, let's say, 1. So there's nothing special about this compared to this. So this is also an area law, but just in one dimension. Any question? Yep. There are, I think for 1D system, you have precise statements about the dimension of A and the dimension of B in terms of Hilbert space dimension. For the 2D case, since there is no mathematical proof, I don't have any rigorous statement about detail, but you have a finite correlation length. So of course, if your system A is too small, right, then you will move away from the area law. So the system size of the system of A has to be big enough compared to the correlation length. And of course, B has to be much bigger than the yeah, I mean, if you look at the entropy as a function of, let's say, the volume, the area of A or the perimeter of A, it will be something smooth. If I take to 0, then the entropy will just be 0. There's no discontinuity in the calculation. So that's a generic statement about gap phases in any dimension. What we want to focus here is we want to focus on 2D topological phases. On 2D topological phases, you can go beyond the area law. You can look at the first correction that you have beyond this term here. So for 2D topological phases. So you still have the dominant term will be linear with the perimeter of your system. And the first correction is actually a constant term, which was gamma. Gamma is called the topological entanglement entropy. And this one is universal. By universal, I mean that the value of gamma only depends on the nature of the excitations that you have in your system. The generic formula for gamma is log d over dA, where d is the square root of the sum over a ta square. So lots of symbols here. dA is called a topological, the quantum dimension associated to one topological sector A. So A, the sum over A is the sum over all the topological sectors. And D is the quantum dimension. So I have one slide, but actually Karian has already done the job this morning to tell you a little bit about the quantum dimension. So the quantum dimension tells you how the internal input space of your excitation grows when you increase the number of excitations. So imagine you have an abelian state. I mean, you have seen the Laughlin state, you have abelian excitations. They have fractional statistic, but still abelian, right? So if you add more and more excitation, there is no internal space like the case of the Moore reed. Of course, the Moore reed's a bit different story. It's a non-abelian state. So somehow, if you want, this quantum dimension tells you how many wave functions you can write down once you have pinned all the excitations. If you take the Laughlin state, once you have pinned all the quasi-holes, the wave function is unique. If you do that for the Moore reed state, that's what Karian was pointing out this morning, you still have some freedom, actually lots of freedom, an exponential number of wave function depending on the number of excitation. So let's say you have nx excitation and you take the Moore reed state. So I just remind you the fusion rule for the Ising part. And the number of fusion trees, so let's say you start with 2 excitation, you can fuse them into the vacuum channel or psi channel. If you have 3 excitation, you can fuse into the first 2 into the one of psi, but then once you fuse with a third sigma, the only option is sigma. When you have 4 so here you have 2 possibilities, and here you have 4, right? So I can now fuse this sigma with another one and get either 1 of psi. So I have to when I give you the wave function, I have to say exactly which fusion channel I pick for my quasi-holes. So the number of wave function, that's what Karian has written down this morning, will grow like up to some factor 2 to the power of the number of excitation divided by 2, so square root of the number of excitation. So the quantum dimension will be square root of 2, log of square root of 2 for this one, square root of 2, yeah. Good. So you can just plug this number here. For the Moore reed state, the fermionic Moore reed state, you have 6 topological sectors, 4 which are abelian. So if you have abelian, the quantum dimension is just 1. It's 1 to the power of no excitation. There is the number of wave function that you can write down does not grow exponentially with the number of excitation. And for the Moore reed state, you get a square root of 2. So the total D for the Moore reed state would be 8. So why do I have, that's for the total quantum dimension. dA, you can always, if you take your system, you can, for example, pick a given topological sector. You don't have to look exactly at the ground state. You can have additional excitations. Adding excitation to your system, if you compute the entropy of the state, plus you have excitation, you have to tell in which topological sector you are. But for the moment, you can forget about this one. So you see that if you're able to compute this quantity, the internal entropy, so let's say you make your numerical simulation and you have the ground state. If you can compute the entropy for various perimeters, so different values of L, if you can check that first, your entropy has to obey the area law, That's the first constraint. And second, if you can extract the topological term here, you can compare with what you get from your model state. If you get log of square root of 8, well, this can be the more rich state. Of course, you can have sometimes you can have states which have the same topology containment entropy, but at least it's a good indication of the phase that you're looking at. But sometimes it's actually quite difficult to do the scaling here, for a simple reason. Once again, you're stuck with numerics. You cannot go to very large system sizes. There's the question of the size of A. So sometimes A will be too small compared to the correlation length, so you will be away from this regime, or A is going to be too big, right? If you go beyond half of the system, you don't get more information. Remember that getting the entropy for A is the same thing that the entropy for B. So it's useless to take A larger than half of the system. And if you do numerics, it's a very strong constraint. And it's sometimes very difficult even to see, for example, the area law in your numerical simulation. So what we will try to do with the story of the entanglement spectrum is actually to try to extract more information, not by computing a single number from the spectrum of the reduced density matrix, but by looking at the full spectrum of the reduced density matrix and try to figure out if it gives us like a fingerprint of the phase we try to identify. And now I will give you one example of a non-trivial entanglement spectrum beyond the spin 1/2 chain. So let's talk about the AKRT spin chain. So AKRT, in case you don't know the acronym, it's for Affleck, Kennedy, Lieb, and Dazaki. So the AKRT chain is one of the simplest n-body quantum systems strongly correlated, where you have a gap phase. So it's a spin, it's anti-ferromagnetic. Spin 1 chain. It's an SPT. So an SPT is a symmetry protected topological phase. That's also one of the simplest examples of SPT. And if you focus on the AKRT, you can write down the AKRT Hamiltonian, which is the sum of the usual Heisenberg Hamiltonian, Sj plus 1. And you also have a quadratic term. It's 1/3 of sum over j, Sj plus 1. You can actually, there is an exact expression for the ground state of this system. So the ground state of the system is a valence bound state. So if you think about your spin 1, these are the spin 1 chain. This is how you can build the ground state of this Hamiltonian. So you start with your spin 1, And now you write each spin 1 as a triplet state using 2 spin 1/2. So let's see, I need some blue and red. Right, so you have to combine these two to get a spin 1. It's just another way to write a spin 1. You write it as 2 spin 1/2, and you project onto the triplet sector. So this guy here is your spin 1. And now what you will do is to project onto the singlet sector the two neighboring spin 1/2, so the red one here and the blue one. So if you write down this wave function, you will get the ground state of this guy. If you have never, this is the first time you see this example, there is like a simple exercise that you can do. Let's say if you take 2 spin 1, right? So if I take 2 spin 1, I can combine them into a spin 0, a spin 1, or a spin 2. Okay. Now you use the usual trick. S1, S2. So if you take S1 plus S2 square, it's 2S1, S2 plus S1 square plus S2 square. So this is the psi 0, it takes psi 1 and psi 2. So you can compute the expectation, the value of S1, S2 when you act on psi 0, psi 1, and psi 2. So I hope I won't screw up the calculation. So if you take this one, so you get 1/2 of 0. This one, this is the spin for the spin 1, so it's 1, 1 plus 1 minus 1. Right? So this gives you 2, 2. So minus 2. So please check that I don't make any mistake here, right? On psi 1. S1, S2 acting on psi 2, it's the same kind of exercise. Now you get 1, 1 plus 1, minus, so it's the same result here, so it gets the minus 4. So it gets minus 2. Which give you the minus 1, psi 2, and S1, S2. Sorry, it's psi, yeah. It's psi 0, psi 0, psi 0, psi 1, psi 1, and now psi 2. It's 1/2 of 2, 2 plus 1, still minus 4, so this is 3, 6, minus 2, 2, so it's plus 1, psi 2. So now if you look at what you get for the expectation value of S1, S2, plus 1/3 of S1, S2 square, writing out psi I, so let's see if I have that in my notes. Otherwise, you can try to do the calculation by yourself. Yep. So you got minus 2/3 for psi 0 and psi 1, and 4/3 for psi 2. So this Hamiltonian actually will project onto, for 2 spin 1, onto the singlet and the triplet sector. These are the two lowest energy state of your problem. So that's exactly what this Hamiltonian will do. It will project onto the, for each pair, you will project onto this triplet and singlet state. So now let's talk about the physical. If you look at the system here, so we will project onto singlet state all these guys here. And you see that you're left with two dangling spin 1/2. One here, the left side, and one here on the right side. So the edge excitation of this system correspond to 2 spin 1/2, one at each end. Right? In 2 spin 1/2, you can combine them into a singlet state and a triplet state. So that's why you get these two guys here. So the AKLT for this system is a gap phase. And if you look at the edge excitation of this gap phase, it's just 2 spin 1/2. We can try to cut the system into two. There's going to be the part A, and there's going to be the part B. So, and we take, so if you have edge excitation here, you will, if you look at the ground state of this guy, it's a four-fold degenerate ground state, right? One singlet and one triplet state. So a total of four ground states. So let's say we pick one. So the one with S equal to 1, and look at the entanglement spectrum. This is the entanglement spectrum when you cut the system into two. This is a numerical calculation where I have started with 8 spin 1, and I trace out half of the system. So this is the entanglement spectrum for the part A, which contains 4 spin 1. Remember, a spin 1, 3 possible states. So the Hilbert space dimension for A is 3 to the power 4. It's 81. So in principle, if you take the reduced density matrix, you should get 81 eigenvalues, whatever they are. Here, if you look at the entanglement spectrum, you observe only 2 levels, which mean that in your reduced density matrix, most of the eigenvalues are 0. Remember that if you have a 0 eigenvalue, since for the entanglement entropy we take minus log, we just put the zeros to infinity. So here you observe all the non-zero eigenvalues of the reduced density matrix. It's much less than what you expect naively. Actually, you can do the exercise, just ask to a monkey to give you a random state and to compute the entanglement spectrum out of that. Well, you will get this kind of crappy result with nothing surprising. You have as many levels as expected, so nothing super fancy here. So that's one key signals. As soon as you compute an entanglement spectrum, and you see that you have much less levels than what you expect, there is something very specific, very profound about the state you're looking at, and I will discuss that in 5 minutes. But then, let me go back to to this guy here. You have 2 levels. Remember, what we have done is to take one of the four ground state of this Hamiltonian here, which means what we have done, we have frozen the edge degree of freedom. What we have done is to, if you take s equal to 1, which is what I've done for this, this plot here, I've picked the two edge dangling spin 1/2 to point up, right? So there is a single wave function. The edge are frozen. They don't matter here. But if I cut the system, basically what I observe is only two levels, which is like for spin 1/2. So, and you can see in this picture, if I cut here, what I will break this pair of spin 1/2. So once again, if I freeze these guys and I cut my system into two by doing this trace, I'm left with this degree of freedom, which is not impaired, now impaired, and which is a spin 1/2. So what you see in the entanglement spectrum of the ground state, it's a many-body wave function, right? The bulk wave function of my system. If I trace out on half of my system and I look at the entanglement spectrum look like the edge spectrum of this guy. And that's one of the key results of all this business entanglement spectrum. Basically, you start from the bulk ground state. And by cutting your system, once again, it's only a single wave function that you have. But you cut your system into two parts A and B. And the information that you extract from the entanglement spectrum is actually the edge spectrum of your physical system. So you can wonder, well, you're cheating a little bit. The AKLT example, it's a very specific wave function, right? I can write it exactly. It's not like, once again, this is, the AKLT is just a prototype of the antiferrometric spin 1 chain. If I only take the Heisenberg part for the spin 1, it's still a gap phase, the same phase. So what's going on if I look at the entanglement spectrum, not of the ground state of this guy, but the ground state of the Heisenberg model? So I just keep this one and throw away the 1/3 in the quadratic term. Well, this is, so that's the difference between random and the AKLT. And now this is the ground state of the Heisenberg model. The same number of spin 1. The same way to cut the system into two. And you can see that, well, you still have two levels here down. Remember that we take minus log. So each time psi is very low, it means that the weight in the density matrix is actually quite high. So the important part of the wave function is on the bottom of the entanglement spectrum. So you have two levels here, and you have a bunch of higher energy, higher entanglement levels. So if you increase the system size, what you will observe is that the gap, the entanglement gap, it's not an energy gap between these two guys here and all the rest, will stay finite when you go to the thermodynamic limit. So the conjecture in that case is to say, well, when you see that, when you have this kind of behavior, so in the entanglement spectrum, you have a low energy structure and entanglement gap that stay finite. When you increase the system size, the universal property that you capture with your state is given by this low energy part of the entanglement spectrum, which is the case for the Heisenberg model, for the spin 1 Heisenberg model. Okay, questions? It's Monday morning, I can understand that. Your jet lag, a bit. Yeah. You have to look at the first excited state in that case. But this, if you do the calculation for the spin singlet, you get exactly the same results. Mm-hmm. The SZA? Oh, remember when I was discussing the spin 1/2 case, I said that SZ is a good quantum number. The total projection of the spin along the z-axis is a good quantum number for the full system. And since I can write it as the sum of the SZ for the part A plus the SZ for the part B, right? I can use the property that I've shown at the beginning of the lecture, that I can use SZA, so the total projection of the spin along the z-axis for the part A, as a good quantum number to label all my states, right? So you have to be careful because you pick it's a spin 1, so there's like a shift of 1/2 that you have to apply if you want to compare really with the spin 1/2. Yeah. The antiferromantic? It is. For the spin 1? No, it's a gap phase. Spin 1/2. The spin 1. You remember this half integer effect? Good. So the last thing I would like to discuss today is what does it mean in terms of computation when the number of levels that you have in your entanglement spectrum is much lower than what you expect naively. And this is tightly related to the notion of matrix product states. Or MPS. So if I have a quantum state, remember I was discussing this psi, which I can decompose onto the many-body basis of all the lambdas. Lambdas are configuration, right? Well, I can always write it like this. Imagine it's, once again, for, let's say, a spin 1/2 or spin 1, if you prefer. Doesn't matter. Mi. So it's like over one configuration. And then I have, well, the many-body state, which is just M1, M2, M3, blah, blah, blah. M. N. So you have n spin 1/2, where mi can be up or down. So that's a many-body basis for my system, right? And I can always decompose any state onto this basis. Do we all agree on that? Good. So now imagine you're a pervert, and you can rewrite these coefficients in a very nasty way. So you can write it as a matrix. It's called B, M1, B, M2, B, Mn, alpha, beta, get M1, Mn, where the B, Mi are matrices. For each side, I need to define a matrix for up and a matrix for down. Are two indices. So for any state, I can always read my decomposition onto this many-body basis as a product of matrices. I have to define two matrices for the example of a spin 1/2. I have to define two matrices, one for the up, one for the down for each side. And for this product of matrices, for any configuration, I pick exactly the same matrix element. So right now, I've done nothing special. Just sounds like a super complicated way to rewrite my coefficients here. So let's say alpha, beta. This one is called the physical index. These are the bond indices. Right, M, so spin up or down, but if you imagine you have electrons on a lattice, it will be just 0 if you have no electron, or 1 if you have one electron. But alpha and beta for the timing is just some indices for my all my matrices, and alpha and beta goes from 0 to chi, where chi is the bond dimension. It's called the bond dimension. It's just the dimension of the matrix. So now, right now it's just rewriting. So of course the goal here, I can always do that. If I pick the right bond dimension for any state, I can rewrite my coefficients like this. Of course, the game here is you have your Hilbert space dimension. This one grows exponentially with the number of spin, or the number of sites. What I would like to do is to get the bond dimension to be much lower than the dimension of the Hilbert space. And I also would like to use exactly the same matrix for any state for any site that I look at. In that case, if I can use chi, let's say, a bond dimension to be on the order of 2 or 3, and I can use only, like, let's say, two matrices, one for the up, one for the down, no matter which site I'm looking at, then of course I will encode all the information about my state in just two 2x2 matrices. And just as an exercise, you can look at the AKRT example. So now M will be +1, it's a spin 1. So the physical index can take 3 different values, plus is equal +1, 0, or -1. And to rewrite the ground state of the AKRT Hamiltonian, I just need these 3 matrices. So if you use these 3 matrices, no matter how many spin 1/2 you have in your system, you will be able to write down the decomposition of the AKRT ground state just using some matrix multiplication. Just to convince you that I'm not lying here, I can So for 2 spin 1, you can look at the ground state of the AKRT in the triplet sector with S equal to 1. The state has only decompose only on these two guys. And now, if you, let's see, if you take the product of B1 and B0, so let's do that. If we take the product of B1 and B0, you get, first you get 0, then you get square root of 2 over 3. The next one will give you 0 and 0. Right? Now you can do the same exercise for B0, B1. It's going to be easier in this way. So it's 0 minus square root of 2, 3, 0, 0. So up to some normalization factor, you will get, so up to this 3/2 factor, that just normalization of the wave function that you have to rewrite, but you get this relative sign plus and minus. And actually, if you compute any product, so you have to pick the matrix element. Remember, that was when I was writing down psi, we have to decide at the very end which alpha and beta you pick. So here you pick alpha equal to 1, beta equal to 2. It's like fixing the boundary condition of your system. So when you have this product of B matrices, you have to pick one matrix element at the very end for any of the coefficients, right? But the same at whatever the configuration you look at. And it's really like fixing looking at different boundary conditions. Since it's a 2x2 matrix, you have 4 possibilities, and you will recover this way the 4 states. If you do, let's say B1, B1, this will give you 0. If I don't screw up. Yep. So you see that, I mean, remember in this formula for the matrix product state, you have to sum over all the configurations. But if you pick this index, the only two product of two matrices which give you a non-zero result are these two guys. So if you want to have fun, you can do this exercise, check that it's true. You can also do that for all the other ground state for the two spin 1, and you will see that it works perfectly. At this point, the question you should wonder is why these structures for the B matrices? Why it's not a 10 by 10 matrix? Why does it? I don't have to increase the size of B if I increase the number of spin 1. Why is it always a 2 by 2 matrix I have to consider? And I think it's the perfect time to stop here, and tomorrow we'll resume there, and I will show you the relation between the entanglement spectrum and the matrix product state. And just to give you the picture, you will see that the number of levels that you have in the entanglement spectrum tells you which size you have to pick, which bond dimension you have to choose for your B matrices. Good. Any questions? Well, if not, let's lunch. Yeah.
So, as you wrote this, if I take a chi-dimensional matrix to be 1, that will imply factorization of this coefficient, which is not at all clear. So, in general, I would expect that chi grows exponentially with the size of the system.
Right.
As the basis of coefficients.
Exactly. Yeah. Exactly. For the IKLT example, it's 2. The size chi is 2, whatever the number of spins, the number of spins that you have in your system. Well, it's not just because you're it's a gap phase, so all the entanglement entropy is constant. And basically, the bond dimension is related to the entanglement entropy. It's the exponential. It's all the other, well, you have to be careful. It's all the other of the exponential of the entanglement entropy. So if the entanglement entropy is constant, then chi is a constant. If you have an area law, you will get something that grows exponentially, but with the perimeter of the system, not the volume. So that's why there is a gain to look at matrix product state, even for a two-dimensional system. Exact diagonalization, for example, is an algorithm that grows exponentially with the volume of your system, the number of sites, the number of particles. The MPS for a 2D topological phase will still grow exponentially. You won't find the exponential in this way, but you have a big gain. It's a gain where you move from the exponential of volume of the system to the exponential of the area of the system. So that's why it's really efficient to work with MPS. MPS is also related to DMRG, density matrix formation group. It's just a modern way to rewrite. MPS is just a modern way to talk about DMRG. No, it's an exact statement. For this model state, it's an exact statement. You can take whatever you want. You can do the exercise for, in the notes I have the example for 3-spin 1. It works. It's like exact statements, just the exact number that you should get for the wave function. There is no approximation here. Yep.
Sorry, is this related with the structure, the way of solving the ground state, which is made starting from a spin 1 half, spin 1 divided into spin 1 half state?
Right, right. Exactly.
That reason why it is two-dimensional matrix speed.
Exactly. So that will show you the derivation tomorrow. Basically, you can relate, it's quite easy to relate the MPS to the entanglement spectrum. And as we have shown you, the entanglement spectrum, wherever you cut in your system, if you take the ground state of the IKLT, you get only 2 levels, because this is the dangling spin 1 half that you have. Right? You cut one of the singlets into 2. That's why you're
Then can you generalize it? I assume you can generalize a situation where you can't really apply this technique of separating a spin 1 into spin 1 half. That must be more powerful.
Yeah, it's once again, it's just a simple example for MPS. Usually if you have a microscopic model, let's say even the Heisenberg model, right? The Heisenberg model, there is no way you can write down the exact ground state, analytically for any system size. I can still do numerical simulation, and I can do DMRG. The DMRG is just an algorithm that works within the framework of MPS. So it looks for an MPS that minimizes the energy of my system. And in principle, if you now look at the entanglement spectrum, well, you get more levels, which means that chi will have to grow a little bit with the system size. But as you know, if you do DMRG for, I don't know, like for the spin 100 spin, you have the Holden gap with very large accuracy. So you don't need to increase, and I don't remember how many states you have to keep in your DMRG, but it's not like a large number.
Going back to the previous chapter on the entanglement spectrum and degeneracy, if you take a different combination for a ground state compared to one of the degenerate one, but you take a combination of those, then the feature will be spoiled, I suppose. In that case, you have a superposition of the bonds and so on by cutting.
Yeah, you will recover you will get 4 states. Basically, if you take a linear combination of for the IKLT, we can discuss about more generic cases, but for the IKLT, if you take the 4 states, so what you have to write down in that case is this kind of full density matrix. So you take the sum of all the projectors. There's a 1/4 factor, right? 4 states. If you take this guy, you look at the entanglement spectrum, you will get 4 levels, whatever the system size. Basically, when you do that, you also have now the degree of freedom of the edge that will play some role. So you will intertwine the degree of freedom that you have by this fictitious edge that you have created by tracing out half of the system and the real edge degree of freedom. So you have two spin one half, you combine them, you get 4 states. And you will get 4 levels in your entanglement spectrum. So you don't spoil it a lot. Actually, you can still keep track of the structure of the edge mode doing that kind of calculation. It works also for more complicated cases where you have, like, take a topological phase, for example, and on the torus, where if you move away from the SPT, you will get something where the degeneracy will increase with the genus of the surface. So Laughlin state you have 3 states. If you use this kind of trick, you will recover lots of information in a very proper way without spoiling out the nice structure that you get for a single state. Lunchtime.